Welcome to underdamped free systems. So recall, if a system is underdamped, and free, then the general solution for displacement was y is equal to C1 e to the negative c over 2m times t cosine of omega naught t plus C2 e to the negative c over 2m t sine of omega naught t, where here omega naught is the square root of 4mk minus c squared all over 2m. So we had this sort of general solution we found previously. We can go ahead and write this in another form similar to what we did previously. So let's go ahead and rewrite C1 and C2 in polar form. So we'll take R to equal the square root of C1 squared plus C2 squared. And we will take, we'll have phi such that C1 is equal to R cosine phi, and C2 is R sine phi. Then just like we did previously, we know that C1 cosine omega naught t plus C2 sine omega naught t can be rewritten as R times cosine of omega naught t minus phi. And so what this gives us then is y is just e to the negative c over 2m t times that C1 cosine omega naught t plus C2 sine omega naught t. This is the same thing as R e to the negative c over 2m t times cosine of omega naught t minus phi. So what we have here is we have our amplitude changes with time. So we call R e to the negative c over 2m t, the time varying amplitude. Amplitude. As time passes, that will go to 0. We have frequency equal to omega naught. And then we also will have a period, which we will now call the quasi period. Of 2 pi over omega naught. So the reason we refer to it as the quasi period here is because we are not identically repeating the same pattern since our amplitude is shrinking. But it's essentially the same concept. It's just a period but with amplitude shrinking. So the graph doesn't look identical to itself. So let's go ahead and take a look at an example. So this time we're going to work with feet and pounds so we can see our alternative unit systems. So let's suppose a 16-pound object stretches a spring 0.8 feet in equilibrium, and the system has a damping coefficient of 6 pounds for every foot per second of velocity. The object is initially displaced 1 foot above equilibrium and is released with an initial velocity of 0 feet per second. And our job is to find the displacement function and then identifying the time varying amplitude, the frequency, and the quasi period. So just a note, 16 pounds is not the mass. It is actually our force. So to find mass, we will do m is equal to the pounds divided by g, our acceleration due to gravity. Here, g is 32 feet per second squared. And this will give us the mass in slugs. So in this case, we have our mass. We have 16 pounds divided by 32 feet per second squared. And so we wind up with 0.5, what are called slugs. This is our mass when we are working with pounds. Then we can go ahead and find K. So to find K, we will once again do K times the equilibrium stretch L, or delta L, is equal to m times g. Note this m times g is actually that 16 pounds. So we have K times, in this case, we stretched by 0.8 feet. Let me update my screen. Again, we have K times 0.8. That was our equilibrium stretch in feet. And this should equal that 16. M times G is just the pounds. So in this case, then we get that our K is 16 divided by 0.8, which is just 20. We were told that C is equal to 6, and then we have no external force. So we have our equation would be M, it was 0.5 y double prime plus 6y prime plus 20y is equal to 0. And then for our initial conditions, our initial displacement was an upward displacement of 1 foot. So make sure this is the displacement in feet. And then y prime of 0 was 0. Again, this should be in feet per second. So we need to solve this system. So the characteristic, so solving the IVP. We have characteristic equation. 0.5 r squared plus 6r plus 20 is equal to 0. You can do quadratic formula or you can complete the square, whichever one you want to do. If we complete the square, I'm going to rewrite this as r squared plus 12r plus 40 is equal to 0. This would be r plus 6 squared to get the r squared plus 12r. That contributes plus 36. We're missing a plus 4 or a plus 2 squared. This is equal to 0. So we get then that r is equal to -6 plus or minus 2i. So we have general solution. Y is equal to C1 e to the -6t cosine of 2t plus C2 e to the -6t sine of 2t. Solving for our initial conditions, y of 0 equaling 1, this would be just C1 is equal to 1. And then, so we have y is equal to e to the -6t cosine of 2t plus C2 e to the -6t sine of 2t. If we take the derivative of that, we would have -6 e to the -6t cosine of 2t minus 2 e to the -6t sine of 2t, product rule in the first term. And then we would have plus C2 times -6 e to the -6t sine of 2t plus 2 e to the -6t cosine of 2t. Note that C2 minus multiplies both of those last two terms. So if y prime of 0 equals 0, that first term is -6, the second term and third term go to 0, and then we have plus 2C2. So this would mean that C2 would have to equal 3. And so our solution would be y is equal to, C1 was 1, e to the -6t cosine of 2t plus 3 e to the -6t sine of 2t. And then we can rewrite this. So rewriting this, we have r is the square root of C1 squared plus C2 squared, or the square root of 1 squared plus 3 squared. And we get r is square root 10. And then phi satisfies uh, 1 is equal to square root 10 times cosine of phi. That's C1 is equal to r cosine phi. And C2 is r sine phi. So we have 3 is equal to square root 10 sine of phi. So we get cosine of phi is 1 over root 10. Sine of phi is 3 over root 10. These are both positive. So we're in the first quadrant. And so we can just use phi is the principal angle inverse cosine of 1 over root 10, which winds up being about 1.249. You don't actually need to solve for phi explicitly if you don't want to. It's not required for our time varying amplitude or our frequency or quasi period, but we can rewrite it fully if we want. So we get that y is equal to the square root of 10 times e to the negative 6t times cosine of 2t minus 1.249 ... So our time varying amplitude this is that r e to the negative c over 2m t. This is just square root 10 e to the negative 6t. Our frequency is just omega naught, so 2. I should say our units for the amplitude are feet. Our units for our frequency are seconds. And then our quasi period we are looking at, sorry, our quasi period is 2 pi over omega naught, or 2 pi over 2, or just pi. The quasi period is in seconds. The frequency is cycles per second. So again, essentially we have our exponential decay on our sort of amplitude for our oscillations, but we do have oscillations going on. So this is just a little more detail in studying what is happening in that underdamped case.